Buried in rock that formed nearly 3 billion years ago, there are chemical fingerprints that should not exist. Traces of life woven into stone older than almost anything on the planet. Not bones, not shells, not anything you could hold in your hand. Just faint signatures, whispers left behind in the oldest layers of Earth, hinting that our world was already alive when it was still cooling from its violent birth. And the deeper scientists dig, the stranger the story becomes. Because the timeline keeps sliding backward, closer and closer to a moment when the planet should have been far too hostile for anything to survive. This is why some researchers now speak about Earth's earliest history in almost hushed voices. Something took hold on this planet with a speed that our understanding of biology struggles to explain, and whatever it was, it arrived so early that the rocks recording its presence barely survived the fury of the young world around them. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand why this is so unsettling, you have to travel back to a version of Earth that would be completely unrecognizable to you. Roll the clock back 4.5 billion years. The planet is barely finished forming. It is a churning ball of molten rock and metal, glowing a dull red in the darkness. There are no oceans. There is no breathable air. The sky, if you could call it that, is a suffocating haze of carbon dioxide, nitrogen, water vapor, and toxic gases venting from countless volcanoes. The surface is not solid ground, but a shifting crust that repeatedly cracks, melts, and reforms. And hanging above all of it, the young sun burns with a strange, pale light, fainter than the sun you know today. This is one of the quieter puzzles of the early Earth, and a genuinely strange one. When the sun was young, it was noticeably dimmer than it is now, shining with significantly less warmth than it does today. By all rights, that should have left the early Earth frozen solid, locked in a deep and permanent ice age, its oceans turned to sheets of ice from pole to pole. And yet, all the evidence suggests that the young Earth was not frozen at all. It had liquid water. It was warm enough for the chemistry of life to unfold. How could the planet stay warm under a fainter sun? The most likely answer is that the early atmosphere was rich in gases that trapped heat far more effectively than our air does today, wrapping the young world in a thick, warming blanket. As the sun slowly brightened over billions of years, the composition of the atmosphere shifted in step, keeping the planet within the narrow band of temperatures where liquid water can exist. It is a delicate balancing act, one that has continued for almost the entire history of the Earth, and one that life itself has helped to regulate. That the planet threaded this needle for so long, staying habitable across billions of years of change, is one more reason the story of Earth feels almost improbably fortunate. This is the world where the story begins, a place so hostile that standing on its surface would have vaporized you in an instant. Try to picture it properly. The ground beneath your feet would not be ground at all, but a restless skin of half-solid rock, cracking apart to reveal rivers of glowing magma underneath. In places, oceans of molten rock would stretch to the horizon, their surfaces rippling with heat, venting plumes of scalding gas into a sky choked with ash and vapor. The air would be thick enough to feel like a physical weight, a suffocating mixture that no living thing you know could breathe for even a moment. There would be no bird song, no wind through trees, no lapping of gentle waves. Only the deep, grinding rumble of a planet still forming, punctuated by the roar of eruptions and the distant thunder of objects falling from the sky. And above it all, hanging in a hazy, reddish heaven, would be a moon far closer and far larger than the pale disk you know today. In those early days, the moon orbited much nearer to the Earth. Looming enormous overhead, its gravity tugging at the molten surface and raising tides in the seas of lava. It would have dominated the sky, a vast and menacing companion born, most scientists believe, from a colossal collision early in Earth's history. For a young Earth, this was not a peaceful cradle. It was a forge, a place of heat and pressure and relentless violence, hammering the raw material of a planet into shape. And it is here, in the middle of this forge, that the story of life may have begun. For a long time, scientists assumed that life could not possibly have existed during this era. The very name they gave to this chapter of Earth's history tells you everything about how they imagined it. They called it the Hadean, named after the ancient underworld, a realm of fire and shadow. It was supposed to be a dead time, a lifeless prelude, hundreds of millions of years of nothing but heat and violence, before the planet finally settled down enough for biology to take its first tentative steps. That was the comfortable story. That was the version that made sense. And then the rocks began to contradict it. It is worth appreciating just how deeply that reversal cut against expectation. The whole point of calling this era the Age of the Underworld was to signal that nothing could live there. It was meant to be a barren prelude, a dead stretch of time that had to be endured and survived before the real story of life could begin. Scientists were not looking for life in these rocks. They half expected to find nothing at all, only the sterile chemistry of a lifeless young planet. And instead, again and again, they found hints that something had been there, faint chemical signatures where there should have been none. Structures that resembled the work of living communities in rocks that were supposed to predate life entirely. The evidence did not arrive all at once, in a single dramatic discovery. It accumulated slowly, finding by finding, each one adding to a growing sense that the old story was wrong. The dead age was not so dead after all. Something had been stirring in the fire, far earlier than anyone had dared to suppose, and with each new discovery, the moment of life's true origin retreated deeper into the past, closer and closer to the violent birth of the planet itself. The problem with studying the earliest Earth is that almost none of it survives. Our planet is restless. Its surface is constantly recycled, dragged down into the interior at the boundaries of tectonic plates, melted, and pushed back up somewhere else. Mountains rise and erode away, oceans open and close. Over billions of years, this endless churning has erased nearly all of the original crust. This restlessness is, in a way, the price we pay for living on a geologically active world. The very same processes that erase the ancient record are also the ones that make the Earth habitable in the first place. The slow churning of the interior helps regulate the planet's temperature over immense spans of time. It recycles the chemicals that life depends on, dragging them down into the depths and returning them to the surface. It builds the continents, raises the mountains, and drives the great cycles that keep the planet alive and changing. A dead, still world might preserve its ancient rocks perfectly, but it would also be a world where little ever happens, where the chemistry of life has no engine to drive it. The Earth's restlessness is both a curse and a blessing. It has stolen the earliest pages of our history, but it may also be one of the reasons there was any history to record at all. Finding a piece of rock from the first few 100 million years of Earth's existence is like finding a single page from a book where almost every other page has been burned. And even the pages that survive are charred and faded, their words half erased by the passage of time. To read them at all requires extraordinary patience, ingenuity, and care. Scientists must treat these ancient rocks almost like sacred texts, coaxing out every last fragment of meaning, cross-checking each reading against every other. aware that a single misread clue could send them chasing a false story for years. And yet, in a handful of places scattered across the globe, fragments have survived. In the ancient heart of Greenland, in the weathered outcrops of Western Australia, in the frozen edges of northern Canada, there are rocks so old they predate almost every geological process you learned about in school. These are the closest things we have to time capsules from the infant Earth. You might wonder how anyone can possibly know that a rock is billions of years old. It is a fair question, and the answer is one of the quiet triumphs of modern science. The trick lies in the fact that certain elements are unstable. Over time, atoms of these unstable elements slowly transform into atoms of other elements at a rate that is fixed and unchanging, like the ticking of an impossibly steady clock. Each of these natural clocks ticks at its own particular speed, some fast, some agonizingly slow. When a rock forms, it locks a certain amount of these unstable atoms inside it. From that moment on, the clock starts running, and the unstable atoms begin their slow transformation into their more stable products. By measuring how much of the original element remains, and how much has transformed, scientists can calculate exactly how long the clock has been running. In other words, they can read the age of the rock. The slowest of these natural clocks tick so gradually that they can measure spans of billions of years with remarkable precision. It is thanks to these clocks that we can say, with real confidence, that a given fragment of Greenland is nearly 3,800,000,000 years old, or that a tiny Australian crystal formed more than 4 billion years ago. Without this ability to read the ages of rocks, the entire deep history of the Earth would be a blur. With it, we can place events in order across billions of years and begin to reconstruct the story of our planet from its very beginning. These are the closest things we have to time capsules from the infant Earth, and when scientists began to examine them carefully, they found something they were not expecting. It is worth pausing to appreciate just how extraordinary these surviving rocks are. The oldest fragment of the Earth ever found is not even a rock in the usual sense. It is a single, microscopic crystal, a grain of a tough mineral called zircon, discovered in the hills of Western Australia. Zircon crystals are almost indestructible. They can survive being weathered out of one rock and locked into another, again and again, across billions of years, carrying their internal clock intact the whole time. And this particular grain has been dated to an astonishing age, roughly 4,400,000,000 years old. That means it formed when the Earth was barely 100 million years old, in the very heart of the Hadean, the supposedly dead age of fire. And the chemistry locked inside that ancient crystal tells a surprising story. It suggests that at that impossibly early time, there may already have been liquid water on the surface of the Earth. Not oceans of lava alone, but actual water, cool enough to interact with the crust and leave its fingerprint in the growing crystal. This single grain quietly overturned an entire assumption. The early Earth may not have been an unbroken hellscape from pole to pole. There may have been calmer regions, pockets of liquid water, places where the temperature dropped enough for the chemistry of life to at least become possible. And if there was water that early, then there was a stage on which the drama of life could begin far sooner than anyone had dared to imagine. With that in mind, the scientists returned to the oldest rocks with sharper questions. Consider the rocks of southwestern Greenland, in a region known as Isua. These formations are around 3,800,000,000 years old. They formed when the Earth was still incredibly young, still being battered by debris left over from the birth of the solar system. And locked inside them are tiny particles of graphite, a form of carbon. Now, carbon by itself is not remarkable. It is one of the most common elements in the universe. But carbon comes in different varieties, called isotopes, and the ratio between these varieties can act like a signature. Living organisms have a subtle preference. When life builds its cells, it slightly favors the lighter version of carbon over the heavier one. This preference leaves behind a distinctive imbalance, a fingerprint that non-living chemistry does not usually produce. It is a subtle thing, this preference, but it is remarkably reliable. When you analyze a leaf, a bacterium, a fragment of wood, or the tissue of an animal, you find the same characteristic tilt in the balance of carbon, the mark of life's gentle bias toward the lighter form. It is one of the most useful tools scientists have for detecting the presence of life, past or present. And because it operates at the level of atoms, it can persist even when every other trace of an organism has vanished. The body decays, the structures collapse, the cell disappears entirely. But the altered balance of carbon can remain, locked into the rock, a chemical ghost of something that was once alive. This is why the carbon signatures in the most ancient rocks carry such weight, and why they provoke such intense debate. They are, in effect, the faintest possible echo of life, a whisper preserved in stone long after everything else has been erased. And in those ancient Greenland rocks, the graphite carries exactly that kind of imbalance. The lighter carbon is enriched in precisely the way you would expect if it had once passed through something alive. To understand why this matters so much, it helps to know how these isotopes behave. Carbon in nature comes mostly in two stable forms. One is slightly lighter, one is slightly heavier, and the two are otherwise chemically identical. When life takes carbon from its environment to build its cells, the delicate machinery inside it moves the lighter version just a fraction more easily than the heavier one. It is a subtle bias, but it is remarkably consistent. Wherever life is at work, it leaves this same tilt in the balance of carbon, a fingerprint so reliable that scientists use it routinely to detect the presence of biology. Now, there are non-living processes that can shift the carbon balance too, and this is exactly why the debate around the Greenland graphite is so fierce. But the degree of the shift, the specific pattern of enrichment, sits squarely in the range that life produces. For many researchers, that is enough to make the hairs on the back of their necks stand up, because it means that in rock nearly 3,800,000,000 years old, on a world barely settled from its formation, something was already sorting carbon the way only life is known to do. Let that settle for a moment. 3,800,000,000 years ago, on a planet still cooling from its formation, something was already pulling carbon out of its environment and using it. Something was already alive, or at least, something was doing the chemistry that only life is known to do. And Greenland is not alone. In the rocks of Western Australia, in a region called the Pilbara, scientists found structures that look eerily like the work of living communities. These are called stromatolites. To understand what they are, picture a shallow sea, warm and still, its floor coated with sticky mats of microscopic organisms. As sediment drifts down through the water, it settles onto these mats and gets trapped. The organisms grow upward toward the light, building a new layer on top of the old one. Over centuries and millennia, layer upon layer accumulates, forming dome-shaped or column-shaped mounds of finely banded rock. Stromatolites like this still form today in a few rare and salty corners of the world. They are quite literally cities of microbes, monuments constructed grain by living things. If you could stand on the shore of one of these ancient seas and look out across the shallows, you might not immediately realize you were looking at life. You would see low, rounded mounds rising from the water, some smooth, some crinkled, spreading across the seafloor like a strange, silent architecture. They would not move. They would not seem alive in any obvious way. and yet each one would be a living structure, its surface a thin film of countless microbes, quietly building their world one microscopic layer at a time. There is something humbling about the fact that the very first monuments ever constructed on Earth were not built by hands or minds or tools. They were built by organisms too small to see, working together in numbers beyond counting, over spans of time that dwarf the whole of human history. These were the first builders, and their handiwork, hardened into stone, still survives. And in the Pilbara, there are stromatolites that are roughly 3,500,000,000 years old. If these ancient structures were built the same way as their modern counterparts, then thriving microbial communities were already carpeting the shallow seas of the early Earth. The best place to understand what this means is a remote bay on the far side of the world where stromatolites still form today. In a warm, shallow, extremely salty inlet, mounds of layered rock rise from the seafloor, built by the same kind of microbial mats that may have covered the ancient oceans. These living stromatolites are among the closest things we have to a window into the deep past. Standing among them, you would be looking at a scene that has barely changed in billions of years, a living fossil of the way the world once was. The organisms grow, trap sediment, and build their mounds with a patience that spans lifetimes, exactly as their ancestors did long before there were any eyes to watch. Salty, harsh conditions keep other creatures away, allowing these ancient builders to survive in a few rare refuges where nothing else can outcompete them. To look at them is to glimpse the world as it was when microbes ruled unchallenged, when the shallow seas belonged entirely to the invisible multitudes. And it lends real weight to the idea that the layered rocks of the deep past were built the same way, by communities of living things reaching toward the light. Not a single stray cell clinging to survival, but entire ecosystems, layered and organized, spreading across the ocean floor. And notice what that implies. For entire microbial communities to be flourishing that early, life could not have only just begun. An ecosystem is not the mark of a fragile new arrival. It is the mark of something that has already taken hold, already diversified, already spread and settled into its environment. By the time life is building layered cities of microbes across the seafloor, it has clearly been at work for a long while already, which pushes the true origin back further still, into the shadows before the oldest rocks, into a time we cannot see. Every time we find the earliest evidence of life, it turns out to be evidence of life that is already well established, already thriving. We keep arriving at the scene to find that life got there long before us, and long before our oldest rocks, and left us only the faintest hint of just how early it truly began. The picture that emerges is startling. Life was not a latecomer, arriving billions of years after the planet formed. Life was there almost from the beginning, pressing itself into the rock record at the very earliest moment those rocks could preserve it. This completely inverts the old story of a dead young Earth slowly warming into a place fit for life. Instead of life waiting patiently for a gentle, welcoming world, it seems to have appeared almost the instant the planet could support it, in the middle of chaos and violence, and never let go. And this is where the unease begins. Because if life appears in the oldest rocks we can find, then the true origin of life lies somewhere even further back, in a time from which no rocks survive at all. We are seeing the story only after it has already started. The opening chapter is missing entirely. This is one of the cruelest frustrations in the entire search. The single moment we most want to witness, the transition from lifeless chemistry to living biology, occurred in a time from which almost nothing survives. The rocks that might have recorded it have been recycled, melted, and destroyed. Whatever fragile traces the first life left behind were erased long ago. We are left staring at a wall of deep time, knowing that the answer to our oldest question lies just on the other side, in an era we cannot reach. It is a little like arriving at a play after the curtain has already risen, and the story is well underway. We can watch what unfolds. We can piece together some of what must have happened before. But the opening scene, the moment everything began, played out to an empty theater, and no recording of it remains. This is why scientists must approach the origin of life indirectly. They cannot dig up the moment of creation. Instead, they must reconstruct it using every available clue. The chemistry of the oldest surviving rocks, the shared machinery of all living things, the molecules that form in space and in laboratory experiments, the behavior of life in the most extreme environments today. From all of these scattered fragments, they try to build a picture of an event no one witnessed and no rock preserved. It is one of the most ambitious detective stories ever attempted, a reconstruction of the single most important event in the history of the planet, from evidence that is billions of years old and maddeningly incomplete. So how far back does it go? This is where the search leads to some of the most controversial claims in all of science. In northern Quebec, along the shores of Hudson Bay, there's a formation known as the Nouveau Agittouk Greenstone Belt. The rocks here may be among the oldest ever discovered on the surface of the Earth. Depending on how they are dated, they could be anywhere from 3 billion, 700 million to well over 4 billion years old. The uncertainty in that range is itself part of the story. Dating rocks this ancient is extraordinarily difficult because they have been altered so many times over their immense history. Different methods, applied to the same formation, can yield different ages, and scientists debate fiercely over which readings to trust. If the older estimates are correct, these rocks would be among the very oldest surviving pieces of the Earth's original crust, dating almost to the time the planet finished forming. And that is precisely what makes the possible traces of life inside them so provocative. If life was present when these rocks formed, and if these rocks are as old as some believe, then life existed almost as far back as it is possible for surviving rock to record. The very oldest stones we have would then already contain the marks of the living. And inside these rocks, researchers reported finding tiny tubes and filaments made of iron-rich minerals. Structures that, to some scientists, look remarkably like the fossilized remains of microbes that once lived around hot vents on the ancient seafloor. If that interpretation is correct, and this remains fiercely debated, then life existed within a few 100 million years of the planet's formation, possibly earlier, possibly during the Hadean itself, that supposedly dead age of fire and chaos. Think about what that means. The Earth may have still been an ocean of molten rock in places, still being pelted by asteroids and comets, still radiating heat from its formation, and life was already finding a foothold. Not waiting for calm, not waiting for the storm to pass, taking root in the middle of the violence. To understand just how remarkable and how disturbing this is, we need to look at what the young Earth was actually enduring during those first several 100 million years. Because it was not simply hot. It was under siege. The early solar system was a shooting gallery. When the planets formed, they did not sweep up every scrap of material around them. Vast swarms of leftover rock and ice continued to drift through space, and Earth's gravity pulled them in relentlessly. Impacts were constant, small ones, large ones, and occasionally catastrophic ones. In the earliest days, the sky itself would have been a source of constant danger. Streaks of light as debris burned through the thickening atmosphere. Flashes on the horizon as smaller objects struck the surface. And, every so often, a cataclysm as something truly enormous arrived, an impact powerful enough to reshape entire regions of the planet in an instant. the young Earth was still, in a sense, finishing its own construction, sweeping up the last of the material from which it had formed. Each impact added mass, added heat, and stirred the surface into fresh turmoil. For hundreds of millions of years, this bombardment continued, gradually tapering off as the swarms of debris were slowly cleared away, swept up by the growing planets, or flung out of the solar system entirely. But during the height of it, the Earth was anything but a peaceful cradle. It was a target, sitting in a cosmic shooting gallery, absorbing blow after blow as the solar system slowly settled into its more orderly modern form. There is strong evidence that during a stretch of time, roughly 4 billion years ago, the inner solar system experienced an especially brutal barrage. Some scientists call it the Late Heavy Bombardment. During this period, the Earth and the Moon may have been struck by an enormous number of large objects in a relatively short span. You can still see the scars of it on the Moon today. Those dark patches you notice when you look up at the full moon are enormous basins, blasted out by impacts during this violent chapter. The Moon has no weather, no plate tectonics, no oceans to erase its wounds, so it preserves a record of that bombardment that the Earth has long since covered over. Look carefully at the Moon on a clear night, and you are looking at a frozen photograph of that ancient violence. Every crater, every dark basin, is a wound that never healed, a scar left by an impact that happened billions of years ago and was never smoothed away. Now imagine that same rain of fire falling on the Earth. But the Earth was hit too, and being larger, it was hit even harder. Its stronger gravity would have pulled in even more of the debris drifting through the early solar system, drawing the incoming objects toward it like a vast net. For every scar you can see on the Moon, the Earth would have received several more. And the Earth, unlike the Moon, has erased almost all of them, hidden them beneath moving continents and rising seas, leaving us to imagine the scale of the assault from the marks left on our silent, pock-marked neighbor. Some of these impacts were so immense that they could have boiled away entire oceans. Imagine an object dozens of kilometers across slamming into the sea at tremendous speed. The energy released would have superheated the water, flashing it into scalding vapor, filling the sky with a suffocating blanket of steam. The surface would have become a hellscape, the oceans reduced to a thin, boiling remnant or evaporated entirely. For a period after such an impact, the entire planet might have been wrapped in a thick shroud of superheated steam, the surface glowing, the seas gone. It could have taken thousands of years, perhaps far longer, for that steam to cool and rain back down, refilling the ocean basins and allowing the surface to settle once more. During that time, the shallow, sunlit waters where life might have flourished would have simply ceased to exist. Any life clinging to the shallow waters would have been erased in a heartbeat. And yet, there may have been refuges. Deep beneath the surface, far below the boiling seas, in the rock itself, and around the hot vents on the ocean floor, conditions might have remained just survivable. Some scientists suspect that if life did endure these catastrophes, it did so by hiding in the depths, sheltering in the planet's crust, while the surface burned above. When the storm passed and the oceans returned, life could have crept back up from below, recolonizing a world scrubbed clean. In this picture, the deep, dark places of the Earth were not just the birthplace of life, but its bunker, its shelter from the fury raining down from the sky. And here is the part that keeps scientists awake at night. If life had already emerged before one of these ocean vaporizing impacts, it might have been wiped out completely, only to arise again once the planet cooled. This raises a haunting possibility. Life may not have originated just once on Earth. It may have started, been destroyed, and started again, perhaps multiple times, in a brutal cycle of birth and annihilation. There is a particular horror and a particular beauty in imagining this. Each attempt would have represented an entire lost world of life, a flourishing that rose and then vanished without leaving any descendants, erased so completely that we can never know it existed. There could have been whole chapters in the story of life on Earth that were entirely wiped away, forgotten origins that led nowhere, buried beneath the fire and lost to us forever. And yet, against that grim backdrop, there is something almost heroic in the persistence. No matter how many times the planet was scrubbed clean, life kept returning, kept finding a way, kept beginning again, until, at last, one beginning endured and became the root of everything that followed. Each time the planet was sterilized, the clock reset, and each time, somehow, life came back. There is something almost eerie about this picture when you dwell on it. Imagine the young Earth as a stage on which the same drama plays out over and over. Life emerges in some quiet corner, in a warm pool or a deep-sea vent, and begins to spread. Then, without warning, an enormous object falls from the sky. The oceans boil, the surface glows, the stage is wiped clean. Silence returns. And then, once the steam has rained back down and the seas have refilled, life emerges again. Perhaps from survivors sheltering deep underground, perhaps starting entirely anew from the chemistry left behind. If this really happened, then the origin of life may not be a single event we are searching for, but a process that occurred repeatedly, a beginning that was rehearsed again and again until conditions finally settled enough for one attempt to endure. It raises a strange and beautiful thought. The life we descend from may be the last in a long series of beginnings. Not the first spark, but the one that finally caught and held after countless others had been snuffed out. We would then be the heirs not of a single origin, but of a whole hidden history of origins, most of them lost forever to the fire. That resilience is astonishing, and it is not just a feature of the distant past. If you want to understand how stubbornly life clings to existence, you only have to look at where it survives today. Life on the modern Earth has colonized places that seem utterly impossible. In the boiling springs of volcanic regions, where the water is hot enough to cook flesh, there are microbes that thrive, not merely surviving, but flourishing, treating temperatures that would kill almost anything as their preferred home. In the frozen deserts of the poles, in ice that has not melted for thousands of years, there are organisms locked away, waiting. In the most acidic waters imaginable, in pools that would dissolve metal, life finds a way, deep inside solid rock, kilometers below the surface, in total darkness, cut off from sunlight and cut off from the world above. There are microbes living in the tiny spaces between mineral grains. Some of these deep-dwelling organisms may reproduce so slowly that a single generation takes thousands of years, living lives so patient and so slow that they blur the line between living and dormant. In the crushing depths of the ocean, where the pressure would flatten a submarine, life persists. Around the scalding vents on the seafloor, entire ecosystems flourish in perpetual night, powered by chemistry alone. Wherever there is a source of energy and even the faintest trace of water, life seems to find a foothold. This tells us something profound. Life is not fragile in the way we often imagine. Once it exists, it is extraordinarily difficult to stamp out completely. It spreads into every available crack and corner, adapts to conditions that seem lethal, and holds on with astonishing tenacity. If life is this hardy on the Earth of today, then perhaps it is easier to imagine it surviving the brutal conditions of the young planet, hiding in the deep and the dark, while the surface burned, waiting out the catastrophes and creeping back when the danger passed. But it also deepens the mystery. How could something as intricate and improbable as life keep emerging so quickly on a world that kept trying to destroy it? There is a real tension here that scientists have wrestled with for a long time. On one hand, life looks staggeringly improbable. The complexity of even the simplest cell is so great that it seems almost impossible for it to have assembled by chance. On the other hand, the evidence from the ancient rocks suggests that life appeared with astonishing speed at the first possible moment on a violent and unwelcoming planet. These two facts sit uneasily together. If life is so improbable, how did it arise so fast? And if it arose so fast, how can it really be so improbable? One way to resolve the tension is to suppose that life is not as improbable as it first appears. Perhaps, under the right conditions, the raw chemistry of the young Earth was naturally inclined to move toward life, guided by the ordinary laws of physics and chemistry rather than by chance alone. Perhaps the path from simple molecules to living cells is less like winning a lottery and more like water, finding its way downhill, following the natural slope of the chemistry involved. If that is the case, then life may not be a fluke at all, but something close to inevitable wherever the conditions are right. The speed with which it appeared on Earth would then be exactly what we should expect, but this remains a hope, not a certainty. We still do not understand the path well enough to know whether it was inevitable or miraculous. And until we do, the tension remains, a puzzle at the very heart of our own existence. To appreciate the difficulty, you have to understand what life actually requires. Even the simplest living cell is a marvel of staggering complexity. It is not just a blob of chemicals. It is a self-contained machine, wrapped in a protective membrane, running thousands of coordinated chemical reactions, storing information in molecules, copying that information, and passing it on to the next generation. At the center of it all is a molecule you have heard of, deoxyribonucleic acid, the famous double helix that carries the instructions for building and operating every living thing. Alongside it works its close relative, ribonucleic acid, and a whole cast of proteins that act as the workers and machinery of the cell. To grasp the scale of the challenge, it helps to remember that these are not simple molecules. The instructions carried in a living cell are written in a sequence so long and so specific that if you tried to spell it all out, it would fill volume after volume. And this information does not merely sit there. It is constantly read, copied, corrected, and acted upon by an intricate array of molecular machines, each one exquisitely shaped for its particular task. A living cell is less like a simple chemical reaction and more like a microscopic factory, humming with coordinated activity, every part depending on every other. The problem is that these molecules are enormously complicated. They do not simply fall together by accident. Getting from a warm puddle of simple chemicals to a self-replicating, information-carrying, membrane-bound cell is a leap so vast that scientists have spent generations trying to figure out how it could have happened at all. Consider just one piece of the puzzle. For a cell to reproduce, it needs to copy its genetic instructions accurately. But copying those instructions requires a whole set of specialized molecular machines. And the blueprints for building those machines are themselves stored in the very instructions they are meant to copy. It is a puzzle wrapped inside itself. The machinery is needed to read the blueprint, but the blueprint is needed to build the machinery. How could such an interdependent system ever get started when neither half seems able to exist without the other already in place? This is the kind of riddle that has consumed scientists for decades. One elegant idea offers a possible way out. Perhaps, in the very beginning, a single type of molecule played both roles at once. Ribonucleic acid, the close cousin of the more famous double helix, has a remarkable property. It can store information, like a set of instructions, and it can also fold into shapes that let it act like a tiny machine, driving chemical reactions on its own. Some scientists believe that the earliest life may have been built around this dual-purpose molecule, in a chapter of history sometimes called the Age, when this single molecule ruled. In that scenario, life did not need both the blueprint and the machinery from the start. It needed only one thing that could be both at once, copying itself and slowly improving, generation after generation, until the more complex machinery of modern cells gradually evolved around it. It is a beautiful idea, but even it does not fully close the gap. Because that first self-copying molecule still had to arise from simpler ingredients, and how it did so remains one of the great open questions. And they still do not fully know. This is one of the deepest unsolved problems in all of science. It sits alongside the greatest mysteries we know of, questions about the birth of the universe and the nature of consciousness, as one of the fundamental puzzles we have not yet cracked. And in some ways, it is the most personal of them all, because its answer is the story of how we ourselves came to be. We understand a great deal about how life works today. We understand a great deal about how it has evolved and diversified over billions of years. But that very first step, the transition from lifeless chemistry to living biology, remains shrouded in mystery. There are many ideas. Some scientists believe it began in warm little ponds on the surface, where sunlight and lightning drove chemical reactions in a rich soup of molecules. In this picture, shallow pools on the young Earth would have been repeatedly filled and dried by the cycles of rain and evaporation, concentrating their dissolved chemicals with each round. Over countless cycles, the molecules within them could have grown more complex, driven by the energy of the sun and the occasional strike of lightning, until something capable of copying itself finally emerged. Others argue it started in the crushing darkness of the deep sea around hydrothermal vents. Picture the ocean floor, split by cracks, where seawater seeps down toward the hot interior of the planet, gets superheated, and gushes back up loaded with dissolved minerals. These vents create natural chemical gradients, flows of energy and raw material that some researchers believe could have powered the very first steps toward life. There is something deeply appealing about this idea. On the modern seafloor, in the crushing cold and darkness where no sunlight ever reaches, these vents support entire ecosystems that need no sun at all. Strange communities of organisms thrive there, drawing their energy not from light, but from the chemistry of the Earth itself. When scientists first discovered these deep-sea ecosystems, it overturned a long-held assumption. For a long time, it was believed that all life ultimately depended on sunlight, that the sun was the source of energy for every living thing. Then, in the crushing darkness of the deep ocean, explorers found entire thriving communities that had never seen a ray of light and never needed one. At the base of these ecosystems are microbes that harvest energy directly from the chemicals pouring out of the vents, building the foundation of a food web in total darkness. Around them cluster remarkable creatures found nowhere else, entire ecosystems flourishing in one of the most extreme environments on the planet, sustained entirely by the heat and chemistry of the Earth's interior. This discovery transformed how scientists think about where life can exist. If life can flourish in such places today, then perhaps the deep sea was always a haven, a place where the raw energy of the planet could be harnessed and channeled into the delicate work of building the first living things. And crucially, the deep sea would have offered protection. While the surface was being scorched by radiation and battered by impacts, the ocean floor lay sheltered beneath kilometers of water, calm and stable and rich in chemical energy. For an origin of life that had to survive a violent world, few places seem more promising. Still others suggest that clay minerals may have acted as templates, helping to line up molecules into ordered chains. The idea here is that certain minerals have surfaces with regular, repeating patterns, and that these patterns could have served as a kind of scaffolding, gathering scattered molecules and holding them in place long enough for them to link together into longer chains. In this view, the first steps toward the ordered molecules of life may have been assisted by the ordered structure of ordinary rock, and there are even more exotic ideas. But whatever the setting, the central puzzle is the same. Simple ingredients had to organize themselves into something that could copy itself and evolve. For more than half a century, scientists have been trying to recreate these first steps in the laboratory. The story of these experiments is one of the most fascinating in modern science. In the middle of the 20th century, a famous experiment attempted to simulate the conditions of the early Earth in a sealed glass apparatus. Researchers filled it with a mixture of simple gases, thought to resemble the ancient atmosphere, added water to stand in for the oceans, and passed electric sparks through it to mimic lightning. They let this miniature world run for days. And when they examined what had formed inside, they were astonished. The simple ingredients had spontaneously combined into amino acids, the very building blocks of proteins. Life's raw materials had assembled themselves all on their own, from nothing more than gas, water, and a spark of energy. It was a stunning result. It showed that the first steps toward the chemistry of life were not miraculous or improbable at all, but could happen readily under the right conditions. In the decades since, scientists have pushed these experiments much further. They have produced a wide range of the molecules that life depends on, using a variety of settings meant to mimic the different environments of the early Earth. They have coaxed simple chemicals into forming the components of genetic molecules. They have watched fatty molecules spontaneously arrange themselves into tiny bubbles, hollow spheres wrapped in a membrane, remarkably similar to the outer envelope of a living cell. Each of these achievements chips away at the mystery, showing that many of the individual steps toward life are surprisingly easy to reproduce. And yet, no one has ever crossed the final threshold. No one has ever taken lifeless chemicals and watched them cross the line into true, self-sustaining, evolving life. We can build many of the pieces. We can assemble many of the ingredients. But the moment of ignition, the instant when chemistry becomes biology, still eludes us. It is a little like having all the parts of a watch laid out on a table and understanding how each one works, but not knowing how they came to assemble themselves into a ticking whole. The gap between the parts and the living system remains the deepest mystery of all. Simple ingredients had to organize themselves into something that could copy itself and evolve. And the truly unsettling part is how quickly this seems to have happened. If life was already leaving traces in rocks nearly 4 billion years old, and if the planet was being repeatedly sterilized by impacts right up until that point, then the window for life to emerge was astonishingly narrow. Life may have needed only tens of millions of years, perhaps even less, to go from nothing to functioning cells. On a geological scale, that is the blink of an eye. Some scientists find this speed deeply troubling. Because if life emerged so easily and so fast on Earth, one of two things seems likely to be true. Either the origin of life is far simpler than we imagine, some almost inevitable consequence of the right chemistry and the right conditions, or something we do not yet understand gave it a helping hand. And it is this second possibility, this sense that something is missing from our explanation, that leads some researchers into far stranger territory. There is a hypothesis, once considered fringe but now taken seriously by a growing number of scientists, that suggests the raw materials of life, or even life itself, may not have originated on Earth at all. The idea is called panspermia. The word means, roughly, seeds everywhere. It is an old idea, in one form or another, stretching back a long way in human thought. But for most of its history, it was regarded as little more than a curiosity, a fringe notion at the edge of respectable science. That has changed in recent decades, as discovery after discovery has shown just how rich in organic chemistry the universe really is, and just how tough living things can be. The idea now spans a whole spectrum of possibilities, from the modest to the radical. At its most modest, the idea is simply that the building blocks of life, the complex organic molecules, were delivered to the young Earth from space. And this part is not speculation. It is increasingly well supported. When scientists study meteorites that have fallen to Earth, they find astonishing things inside them. Certain meteorites, ancient chunks of rock that formed at the very dawn of the solar system, are rich in organic compounds. They contain amino acids, the molecular building blocks of proteins. They contain components of the very molecules that store genetic information. These are not contaminants picked up after the meteorite landed. They formed out there, in the cold darkness of space, long before they ever reached our world. One meteorite in particular became famous for exactly this reason. It fell in Australia in the middle of the 20th century, and when scientists broke it open, they found it packed with organic compounds. Dozens of different amino acids, many of them not even used by life on Earth, which ruled out contamination and proved that they had formed by natural chemistry in space. Here was direct, physical evidence that the molecular building blocks of biology could assemble themselves without any life involved at all, out in the void, and then be delivered to a planet ready-made. Since then, scientists have found the components of genetic molecules in meteorites as well. The very letters of the genetic alphabet, or their close chemical relatives, apparently forming naturally in the debris of the early solar system. Think about what this means. The ingredients that make you were not all forged on Earth. Some of them drifted here from the depths of space, cooked up in interstellar clouds and delivered by falling stones. You are, in a very literal sense, partly made of material that predates the Earth itself. Space, it turns out, is a vast chemistry laboratory. In the frigid clouds of gas and dust that drift between the stars, complex organic molecules form readily assembled on the surfaces of tiny dust grains, bathed in starlight and radiation. Astronomers have detected an entire menagerie of carbon-based molecules floating in these interstellar clouds. The ingredients of life appear to be scattered throughout the galaxy, cooked up naturally wherever the conditions allow. The list of molecules found drifting between the stars is genuinely astonishing. Simple compounds, of course, but also more complex ones, including relatives of the very building blocks that life on Earth depends upon. These molecules form in the cold, dark clouds of gas and dust that fill the spaces between the stars, assembled slowly on the surfaces of tiny frozen grains, then released back into space to drift and combine. When one of these clouds eventually collapses to form a new star and its family of planets, all of that pre-made chemistry is inherited by the newborn worlds. Every young planet, in every solar system, is likely seeded from birth with a rich supply of organic molecules, the same kind that would one day become important for life on Earth. This means the raw materials of biology are not rare or special to our world. They are everywhere, spread across the entire galaxy, forming naturally in the vast clouds from which all stars and planets are born. The universe, it seems, comes pre-stocked with the ingredients of life. The ingredients of life appear to be scattered throughout the galaxy, cooked up naturally wherever the conditions allow. So when the Earth was forming, it was not starting from a blank chemical slate. It was being showered with organic material delivered by comets, asteroids, and interplanetary dust. The young planet inherited a rich supply of the molecules life would need, gathered from across the solar system and beyond. That alone is a remarkable thought. The chemistry of life may have been seeded from the sky. But some scientists push the idea much further. What if it was not just the ingredients that came from space? What if life itself did? This stronger version of panspermia suggests that living organisms, or something close to them, could travel between worlds. Microbes are astonishingly tough. Some can survive extremes that would obliterate almost anything else. They can endure the vacuum of space, intense radiation, brutal cold, and long stretches without food or water, drifting in a dormant state for immense periods of time. Experiments have shown that certain microorganisms can survive exposure to the conditions of open space for years. Scientists have placed colonies of hardy microbes on the outside of spacecraft, exposing them directly to the vacuum, the radiation, and the temperature extremes of orbit. And when they were brought back and examined, some of them were still alive. There is one creature in particular that has become almost legendary for its toughness. A microscopic animal, barely visible even under magnification, that can survive conditions that would obliterate almost anything else. It can be frozen to temperatures close to the absolute cold of deep space. It can be heated, dried out completely, blasted with radiation, and exposed to the vacuum of space, and it can simply shut itself down, curling into a dormant, glass-like state, waiting. When conditions improve, it revives, unfurls, and carries on as if nothing had happened. Creatures like this can endure being dried out for years, then spring back to life with a single drop of water. They can survive pressures found only in the deepest ocean, trenches, and the near-total vacuum of space. They can withstand doses of radiation that would be lethal many times over to almost any other animal. The secret lies in their ability to shut themselves down almost completely, entering a state so still and so protected that the ordinary rules of survival barely seem to apply to them. If life can be this resilient, then the idea of organisms surviving a journey between worlds, locked inside a protective shell of rock, no longer seems quite so far-fetched. The universe may be far more hospitable to hitchhiking life than we ever assumed. Now imagine an asteroid slamming into a world that already harbors life. The impact blasts debris off the surface, hurling rocks into space at tremendous speed. Some of that debris carries microbes locked inside, shielded from radiation by the rock around them. For most of these fragments, the journey ends in the void. But a few might drift for millions of years and eventually fall onto another world, delivering their sleeping passengers to a new home. We know this kind of rock exchange happens because we have found pieces of Mars right here on Earth. Meteorites blasted off the red planet by ancient impacts, which crossed the gulf of space and landed on our world. Think about how remarkable that is on its own. Scattered in collections around the world are stones that began their existence on another planet. They were part of the Martian surface until a violent impact hurled them off the world entirely, launching them into space at tremendous speed. They then drifted through the void for immense spans of time, following long, looping paths around the sun. until at last their orbits crossed that of the Earth and they fell to the ground. We can identify them because the gases trapped inside them match, with great precision, the atmosphere of Mars measured by our spacecraft. These are not theoretical objects. They are real, tangible pieces of another world that you could hold in your hand. If solid rock can make that journey and survive, then the idea of microbes riding along inside such rocks, shielded from the harshness of space, becomes far more than idle speculation. The natural traffic of material between the planets is real and ongoing. The only remaining question is whether life has ever hitched a ride. If rocks can travel between planets, then in principle, so could the life inside them. This raises a startling question about our own origins. What if life did not begin on Earth at all? What if it began somewhere else, and arrived here already alive, carried in on a fragment of some other world? It would explain the puzzling speed with which life took hold. Life would not have needed to originate here from scratch. It would only have needed to arrive and settle in. Some scientists have even wondered whether Mars, in its distant youth, may have been the true cradle. Because in the earliest days of the solar system, Mars may actually have been a friendlier place for life to begin than Earth was. The young Mars was smaller and cooled faster. It had liquid water flowing across its surface, ancient rivers, lakes, and possibly even seas. And crucially, it may have offered stable conditions earlier than the more turbulent, heavily bombarded Earth. The evidence that Mars was once a wetter, warmer world is written all over its surface. Spacecraft orbiting the red planet have photographed the unmistakable traces of ancient rivers, dried-up channels carved by flowing water, and the outlines of what may once have been lakes and shorelines. Robotic explorers crawling across the Martian surface have found minerals that only form in the presence of water and layered rocks that appear to have been laid down at the bottom of ancient bodies of water. Billions of years ago, Mars may have had a thicker atmosphere, a milder climate, and standing water on its surface for long stretches of time. In other words, the young Mars may have looked far more like a place where life could begin than the burning, battered Earth of the same era. That is what gives the Martian origin idea its unsettling power. If life needed a calm, stable, watery cradle to get started, Mars may have provided that cradle before the Earth was ready. Some researchers have proposed a genuinely unsettling scenario: that life first emerged on Mars and was then blasted into space by an impact, drifting across the solar system until it landed on the young Earth. In this scenario, we are not natives of our own planet. We are immigrants, descendants of Martian microbes that found a new and thriving home on a world that would eventually cool, calm, and blossom into the living planet we know. Try to sit with that idea for a moment. It would mean that the ancestral home of all life on Earth, the true cradle, is not a warm pool or a deep-sea vent on our own world, but a cold, red planet hanging in the sky, now seemingly barren and lifeless. It would mean that when we send our robots to Mars and search its ancient riverbeds, we are not just looking for alien life. We may be looking for our own distant origins, for the place where our story truly began before it was carried here on a fragment of shattered rock. The Mars we see today, dusty and frozen and still, would then be a kind of forgotten homeland, the birthplace of a lineage that went on to flourish on a neighbor world while its own surface fell quiet. It is a strange inversion of everything we assume about our place in the cosmos. We think of ourselves as children of the Earth, but if this idea is right, the Earth was our second home, not our first. It sounds like fantasy, but it is a serious hypothesis, discussed in serious scientific circles, and it cannot yet be ruled out. This is precisely why the search for ancient life on Mars has become one of the great scientific quests of our time. If life did once arise on the red planet, then somewhere in its ancient rocks, there may be fossils, chemical signatures, the preserved remains of a second Genesis. Robotic explorers are, at this very moment, crawling across the Martian surface, drilling into ancient riverbeds and lake floors, searching for exactly these kinds of traces. They are collecting samples of rock and sealing them away, in the hope that one day those samples can be brought back to Earth and studied with the full power of our laboratories. If we were to find evidence of past life on Mars, it would be one of the most momentous discoveries in the history of our species, and it would immediately pose a haunting question. Would that Martian life be related to us, sharing the same deep chemistry, suggesting a common origin and a journey between worlds? Or would it be utterly different, a completely separate invention of life, proving that biology can arise independently, more than once, even within a single solar system? Either answer would reshape everything. If Martian life turned out to be our distant cousin, it would strengthen the idea that life can travel between worlds, and that we ourselves might be descendants of something that began elsewhere. If Martian life turned out to be alien in its very foundations, unrelated to anything on Earth, it would suggest that the origin of life is not a rare miracle at all, but something that happens readily wherever the conditions are right. And that, in turn, would imply that the universe is very likely full of life. The stakes of these dusty rocks and frozen riverbeds could hardly be higher. Nor is Mars the only place we look. Further out in the solar system, there are moons that hide vast oceans of liquid water beneath their frozen crusts. Worlds where a shell of ice conceals a dark sea, kept warm not by the distant sun but by the gravitational flexing of their giant parent planets. These hidden oceans may contain more liquid water than all the seas of the Earth combined, sealed away beneath crusts of ice many kilometers thick. On the surface, these moons appear frozen and dead, cracked shells of ice orbiting far from the warmth of the sun. But beneath that ice, in the perpetual darkness, vast oceans may have been churning for billions of years, warmed from below by the constant squeezing and stretching their orbits produce. At the bottom of those hidden oceans, there may be vents, much like the ones on the Earth's own seafloor, pouring out chemical energy into the dark. If life can begin around such vents, then these frozen moons may be among the most promising places in the entire solar system to look for it. We may be surrounded, closer than we ever imagined, by worlds where life could have taken hold in the deep and the dark, entirely independent of the Earth. Of course, panspermia does not truly solve the ultimate mystery. Even if life arrived here from Mars, or from somewhere further afield, the question simply moves elsewhere. Where did that life originate? You are only pushing the puzzle to another location, not answering it, but it does something important. It cracks open our assumptions. There is a version of this idea that stretches even further, and it is worth mentioning if only for how dizzying it is. Some thinkers have proposed that life might not have originated on any planet within our solar system at all, but could have drifted in from interstellar space, carried across the immense gulfs between the stars. Comets and interstellar bodies could, in principle, ferry dormant organisms or the seeds of life across those distances over vast spans of time. In this most expansive version of the idea, life would be a galactic phenomenon, spreading slowly from world to world, from star to star, seeding whatever fertile ground it happens to land upon. It must be said that this remains highly speculative, far more so than the modest and well-supported idea that space delivers the raw ingredients of life. Most scientists remain cautious, and rightly so. But even the most conservative version of the idea carries a profound message. It forces us to consider that the story of life may be far larger than a single planet, that the origin of life may be a cosmic event rather than a purely earthly one. There is another way to search for the origin of life, and it does not involve rocks or meteorites at all. It involves looking at living things themselves and reading the record written inside them. Every living organism on Earth, from the smallest microbe to the largest whale, is related. We are all cousins, part of a single, unbroken family tree that stretches back through billions of years. You can see this relationship in the deepest workings of life. Every organism you have ever encountered uses the same basic genetic code, the same molecular language to store its instructions. Every one of them runs on the same fundamental chemistry, uses the same basic molecular machinery, and shares a core set of features that could only have been inherited from a common source. This shared inheritance points to a single, astonishing conclusion. Every living thing on Earth today descends from one common ancestor. A single population of organisms that lived billions of years ago, from which all subsequent life is descended. Scientists call it the last universal common ancestor. It is not necessarily the very first life that ever existed, but it is the ancestor of everything that survives now, the trunk from which every branch of the tree of life has grown. By comparing the genetic machinery shared across all living things, scientists can attempt to reconstruct what this ancestor may have been like. The picture that emerges is intriguing. This common ancestor seems to have been a microbe that thrived in hot, chemically active water, possibly around the kind of deep-sea vents where seawater meets the heat of the planet's interior. It appears to have drawn its energy from chemistry rather than sunlight, living in an environment that would seem utterly alien and hostile to us, but which may have been one of the most stable and nurturing places on the early Earth. If this reconstruction is correct, then it lends weight to the idea that life began, or at least took refuge, in the deep and the dark, sheltered from the violence of the surface. But here is the crucial point. This common ancestor was already a fully functioning, sophisticated organism. It already had the complex machinery of life in place, which means it, too, was the product of a long history that came before it, a history we cannot read directly, because everything that branched off earlier has vanished without a trace. Once again, we find ourselves staring at a beginning we cannot quite reach. The tree of life gives us its trunk, but the seed from which that trunk grew is hidden from us. And that possibility, that life may be woven into the fabric of the universe itself, leads to one of the most profound and disquieting questions in all of science. If life took hold so quickly and so stubbornly here, and if the ingredients of life are scattered throughout the galaxy, then why does the universe look so silent? This is where a genuine sense of dread begins to creep in for some scientists. To feel the full weight of it, you have to appreciate just how many worlds there really are. For most of human history, we had no idea whether planets around other stars even existed. The stars were just points of light, and whether any of them held worlds like our own was pure speculation. That changed only recently. In the span of a single generation, astronomers went from knowing of no planets beyond our solar system to discovering them by the thousands. We now know that planets are not rare. They are the rule, not the exception. Most stars, it turns out, have planets of their own, and many have several. When you multiply the number of stars in our galaxy by the number of planets they tend to host, the totals become staggering. There are almost certainly billions upon billions of planets in our galaxy alone, and a meaningful fraction of them orbit their stars at just the right distance for liquid water to be possible on their surfaces, in the comfortable zone where a world is neither scorched nor frozen. That means there are, in all likelihood, billions of worlds in our galaxy, where the basic conditions for life, as we understand them, could be met. And our galaxy is just one of countless galaxies filling the observable universe. The number of potentially habitable worlds across the whole cosmos is a number so vast it defeats the imagination entirely. Now, hold that number in your mind and consider what it implies. The reasoning goes like this. Our galaxy is enormous, containing hundreds of billions of stars. Many of those stars have planets. A great many of those planets sit in the comfortable zone where liquid water could exist. The universe has been around for well over 13 billion years, more than enough time for countless worlds to have formed, cooled, and developed life of their own. And if life emerges as readily as the early Earth seems to suggest, then the galaxy should be teeming with it. There should be worlds beyond counting where life took root long before it ever did on Earth. Some of those civilizations should have had billions of years to advance, to spread, to fill the galaxy with signs of their presence. And yet, when we look, we find nothing. No signals. No structures. No evidence anywhere of anyone else. The universe appears empty. This deafening silence has a name. It is called the Fermi paradox, after the physicist who is said to have captured it in a single haunting question. If the galaxy should be full of life, then where is everybody? The scale of the silence is what makes it so strange. Our galaxy is not young. It has existed for billions of years, and countless stars far older than our sun have shone within it, some with planets that formed long before the Earth even existed. If intelligent life is even remotely common, then somewhere out there, civilizations should have arisen billions of years ahead of us. Given that kind of head start, a determined civilization could, in principle, spread across the entire galaxy in a span of time that is long by human standards, but brief compared to the age of the cosmos. They would not need to travel faster than light. They would only need patience, expanding outward world by world, generation by generation, until their presence touched every corner of the galaxy. By now, the galaxy should bear the marks of such expansion many times over. We should see engineered structures, strange signals, deliberate patterns, some sign that we are not alone. Instead, the sky is quiet. We have listened for signals for decades, sweeping the heavens for any whisper of an artificial voice, and heard nothing but the natural hum of the cosmos. The early Earth makes this paradox worse, not better. Because if the story of the ancient rocks is correct, life is not rare or difficult to start. It is fast, tenacious, and stubborn. It appears at the first possible moment and refuses to be stamped out. If that is true here, it should be true elsewhere. The galaxy should be alive with voices. Instead, we hear only silence. And there is one explanation for that silence that scientists find genuinely terrifying. It is not the only explanation, and it may not be the correct one. But it is the one that casts the longest shadow, and it grows directly out of everything the ancient rocks seem to be telling us. It is called the Great Filter. The idea is this. Somewhere along the vast path from lifeless chemistry to a civilization capable of reaching across the stars, there is a barrier. A step so difficult, so improbable, that almost nothing makes it through. A filter that stops the galaxy from filling with life and intelligence. The question that unsettles scientists is a simple one. Where is that filter? Is it behind us, or is it ahead of us? Everything hinges on the answer. The very same evidence can point in wildly different directions depending on where that barrier turns out to lie. And the story written in the ancient rocks of the Earth turns out to be one of the most important clues we have. If the filter lies behind us, then the hard part is already over. Perhaps the origin of life is the Great Barrier, an event so rare that even though the ingredients are everywhere, the spark of true life almost never catches. In that case, Earth got extraordinarily lucky, and we may be among the very few worlds ever to cross that threshold. That would be lonely, but it would also be comforting. The danger would be in our past. But here is what makes the early Earth so chilling. The ancient rocks seem to be telling us that life is not hard to start. It emerged here almost instantly, on a violent, hostile world, again and again. If the origin of life is easy, then it cannot be the great filter. And if it is not the filter, then the barrier lies somewhere else. Perhaps it lies in the difficult leap from simple cells to complex ones, a transition that on Earth took an astonishingly long time. Perhaps it lies in the emergence of intelligence, or in the survival of civilizations once they gain the power to destroy themselves. Consider how long the journey from simple life to complex life actually took here on Earth. For roughly the first half of the history of life, and possibly longer, the planet was ruled entirely by single-celled organisms. The leap from those simple cells to the complex, elaborately organized cells that make up plants and animals appears to have happened only once, and it took an astonishingly long time. Some scientists suspect that this leap is fantastically improbable, a bottleneck so narrow that on most worlds it simply never happens at all. If that is the case, then countless planets across the galaxy may be carpeted in simple microbial life, teeming with organisms too basic to ever build a telescope or send a signal. Life would be common, but complex life, and the intelligence that can eventually flow from it, would be vanishingly rare. That would be one kind of filter. A door that almost nothing passes through, hidden not at the very beginning of life, but somewhere in the long middle of its story. And there are other candidate filters further along still. Perhaps intelligence itself is rare, an evolutionary accident that only occasionally arises. Perhaps intelligent species usually fail to develop technology, or fail to survive the dangerous era when their technology outpaces their wisdom. And that final possibility is the one that casts a long shadow. If the great filter is not behind us, if the easy emergence of life on the early Earth means the hard part is still to come, then the filter may lie in our future. The silence of the galaxy might be telling us that civilizations rise and then vanish, that something stops them, again and again, before they can spread among the stars, that whatever destroys them may one day come for us. This is not a comfortable thought, and it is worth being clear about why it disturbs scientists so deeply. If the great filter is behind us, it means the hardest, most improbable step in our history has already been taken. We would be rare survivors, having crossed a barrier that stopped almost every other world. The path ahead, while surely difficult, would at least be open. But if the ancient rocks are right, and life is easy to start, then that reassuring possibility begins to slip away. The easier it was for life to begin, the less likely it is that the origin of life was the Great Barrier. And if the barrier was not at the beginning, then it must lie somewhere in the long stretch between simple life and a civilization capable of spreading among the stars. Some of that stretch is behind us, but some of it may still be ahead. The silence of the sky could be a graveyard, filled with the memory of civilizations that rose, reached toward the stars, and then fell quiet, one after another, for reasons we cannot yet see. If that is the shape of things, then the very evidence that most excites us, the evidence that life is common and quick to take hold, becomes a kind of warning. It tells us that the cosmos should be full of neighbors, and that something is keeping it empty. And it invites the most sobering question of all. Whatever silenced them, are we approaching it too? No one can answer that question. The great filter may well lie safely in our past, and the silence may have some gentler explanation. Perhaps intelligent life is simply rarer than the ease of life's origin would suggest. Perhaps civilizations are out there, but so distant or so different that we have not yet learned to recognize them. Perhaps the cosmos is vast enough that even a galaxy sprinkled with life could still appear silent to a young species that has only just begun to listen. We do not know. But the mere possibility that the barrier lies ahead is enough to give the deepest thinkers pause. This is why some scientists look at the ancient story written into Earth's oldest rocks and feel something colder than wonder. Because the very evidence that life is common and resilient is also the evidence that our silence in the cosmos has a darker explanation. But let us step back from the abyss for a moment and return to the rocks themselves. Because even here, on solid ground, the mysteries multiply. Every claim about the earliest life is fiercely contested. The problem is that the oldest rocks are also the most ambiguous. When a rock has been buried, heated, squeezed, and transformed for nearly 4 billion years, its original features become blurred and distorted. The tiny structures that look like fossilized microbes might have been produced by living things, or they might have been produced by purely chemical or geological processes that mimic the appearance of life. The carbon signatures that suggest biology might indeed come from ancient organisms. Or they might, in some cases, be explained by non-living chemistry that we do not fully understand. This is the razor's edge that scientists walk when they study the origin of life. The evidence is real, but it is whispering, not shouting. And distinguishing the faint trace of ancient life from a convincing imitation is extraordinarily difficult. Consider those stromatolites in Western Australia. For years, they were held up as clear proof of early microbial life. Then, some scientists argued that certain similar structures might form without any life at all through the slow deposition of minerals in hot, chemically active waters. The debate has raged back and forth. New analyses, new techniques, and new discoveries continually reshape the picture. Some ancient structures once dismissed as lifeless have been re-examined and found to carry subtle chemical signs of biology after all. Others once celebrated as fossils have fallen under suspicion. It is a story that is still being written and rewritten with every new expedition to the oldest corners of the Earth. The tiny tubes and filaments found in the ancient Canadian rocks tell the same tale of uncertainty. To the scientists who reported them, these structures looked remarkably like the fossilized traces of microbes that once lived around ancient vents, complete with features that resemble the way modern microbes arrange themselves. To their critics, the same structures might have formed through purely chemical processes, mineral shapes that happen to resemble life without ever having been alive. The disagreement is not a sign that the science is broken. It is a sign of just how hard the problem is. We are trying to read the faintest possible signal, preserved for billions of years, in rocks that have been battered and transformed almost beyond recognition. Distinguishing the genuine trace of the most ancient life from a lifeless imitation across such an unimaginable gulf of time is one of the most delicate tasks in all of science. And so the researchers argue and test and refine. They develop new instruments capable of probing individual atoms. They search for multiple, independent lines of evidence that must all agree before a claim can be trusted. They travel to the most remote and forbidding places on the planet, chipping away at the oldest stones on Earth, hunting for the next fragment of the story. Each discovery reopens the debate. Each new technique casts old findings in a new light. It is slow, painstaking, and often frustrating work, but it is how we inch closer to answering the oldest question of all. It is a story that is still being written and rewritten with every new expedition to the oldest corners of the Earth. But through all the controversy, one thing has remained stubbornly consistent. The overall pattern keeps pointing in the same direction, again and again. When scientists find rocks old enough to preserve a record of life, they find hints that life was already there. The evidence for any single site can be questioned, but the weight of all the evidence together is difficult to dismiss. Life appears to reach back nearly as far as the rock record itself allows. Consider what a striking pattern this is. If life had truly begun late, long after the planet formed, then we would expect the oldest rocks to be lifeless, with signs of biology appearing only in younger layers. That is not what we find. Instead, wherever we look at rocks old enough to have preserved a record of life, we tend to find hints that life was already present. The signal grows fainter and more contested as we go further back, but it does not simply vanish at some clear boundary. It fades into the limit of what the rocks themselves can preserve. This is exactly the pattern we would expect if life extended back even further than our oldest rocks, into the vanished era before them. The record does not show us the beginning of life. It shows us only the beginning of our ability to detect it. And that consistency is precisely what makes the mystery so profound. It is worth trying to picture what that earliest life may actually have been like. It would bear no resemblance to the living things you know. There were no plants, no animals, nothing that walked or swam or grew toward the light. The first life was almost certainly a simple cell, or something even simpler, a tiny bubble of chemistry wrapped in a fragile membrane, floating in the ancient waters. It would not have thought, or moved with any purpose, or sensed the world in any way we would recognize. It would simply have done what life at its most basic does. It took in raw materials from its surroundings. It used a source of energy to drive its internal chemistry. It grew, and when it reached a certain point, it divided, making a copy of itself. And crucially, sometimes those copies were imperfect. A tiny error would creep into the instructions, and the offspring would be slightly different from the parent. Most of these changes would have made no difference, or made things worse. But occasionally, one would make an organism just a little better at surviving, at gathering energy, at reproducing. And those better-equipped organisms would leave more descendants. This is the engine that has driven the entire history of life. From that first, humble beginning, this simple process of copying, varying, and selecting has, over billions of years, produced everything. Every forest, every coral reef, every bird in flight, every human mind capable of pondering its own origins. All of it flows from those first fragile cells, quietly copying themselves in the waters of a world of fire. The most powerful force in the living world is not strength or intelligence or size. It is simply the ability to make more of yourself and to change a little in the process. And that ability was there almost from the very beginning. Now consider one more strange twist in the story. For most of Earth's history, life was invisible in the ordinary sense. For billions of years, the entire biosphere consisted of nothing but microscopic organisms. Single-celled life, and nothing more. No plants, no animals, no creatures you could see with the naked eye. Just an unimaginable multitude of microbes dominating every corner of the planet, filling the oceans, coating the rocks, drifting through the ancient atmosphere. They were not passive either. They were endlessly inventive in their own quiet way. Over the vast stretches of time they ruled, microbes discovered how to harness sunlight, how to draw energy from minerals, how to breathe substances that would be lethal to us, and how to survive in almost every conceivable environment. They developed the fundamental chemical tricks that all later life would inherit, working out, through countless generations, the basic machinery of living. Every major innovation that complex life depends upon was, in some form, first pioneered by these microscopic organisms long before anything larger existed. By the time the first complex, visible creatures appeared, the microbes had already done the hard work of inventing life's essential toolkit. The animals and plants that would follow were, in a sense, building on a foundation laid down over billions of years by organisms too small to see. We tend to think of the history of life as the history of the large and the visible, the great procession of creatures we can picture. But the true story is overwhelmingly a microbial one, and we are latecomers to a world the microbes had already been shaping for an eternity. This microbial world lasted for an almost incomprehensible stretch of time. If you compress the entire history of life on Earth into a single day, complex, visible life would not appear until the evening. For the vast majority of that day, life was purely microscopic. Let that scale sink in for a moment. Imagine the whole story of life on Earth playing out across 24 hours, from the first stirrings of biology at the stroke of midnight. For hour after hour, morning into afternoon, there is nothing to see but an invisible world of microbes. The oceans teem with them, the rocks are coated with them, the atmosphere is slowly being transformed by them, but to any eye, the planet would look barren and empty. The first complex, visible creatures do not appear until the evening of that imaginary day. Fish, plants, and forests arrive later still. The dinosaurs, which feel to us like the epitome of ancient life, do not appear until the final hour or so. And human beings, our entire species, our whole history, everything we have ever done, would occupy only the last few seconds before midnight. We are a footnote at the very end of a story that is overwhelmingly a tale of the invisibly small. The true rulers of this planet, measured by time, have always been the microbes. They were here first, by an enormous margin, and they built the world that everything else would inherit. And during that long reign of the microbes, something extraordinary happened. The tiny organisms began to change the planet itself. Certain microbes evolved the ability to harness sunlight, using it to power their chemistry. As a byproduct of this process, they released a gas that had been rare in the early atmosphere: oxygen. At first, the oxygen was absorbed by rocks and dissolved minerals, locked away almost as quickly as it was produced. But over vast stretches of time, it began to build up. Slowly, the atmosphere transformed. An air that had been dominated by other gases gradually gained the oxygen that would one day make complex life possible. This transformation was so profound that scientists sometimes describe it as the moment the world changed forever. For many of the organisms that existed before it, oxygen was not a gift. It was a poison. The rise of oxygen may have been one of the most dramatic upheavals life ever experienced, reshaping the entire biosphere and setting the stage for everything that followed. We can actually read the record of this transformation in the rocks. For long stretches of the early Earth, iron dissolved freely in the oceans, because there was no oxygen around to react with it. But as oxygen began to accumulate, it combined with that dissolved iron and pulled it out of the water, causing it to settle to the seafloor in vast layers. Over immense spans of time, these layers built up into striking, banded formations of iron-rich rock. Alternating stripes laid down as the oxygen levels rose and fell. Much of the iron that industrial civilization has mined and used to build its cities comes from these ancient deposits. Every steel beam, every iron tool, is in a sense a gift from those first oxygen-producing microbes who rusted the oceans of the early Earth billions of years before anyone was around to notice. And the change did not stop at the oceans. As oxygen filled the air, it also gave rise, high in the atmosphere, to a protective layer that would shield the surface from the harshest radiation of the sun. That shield would one day make it possible for life to leave the safety of the water and venture onto the land. In this way, the invisible labor of ancient microbes prepared the world for everything that came after. The rise of oxygen may have been one of the most dramatic upheavals life ever experienced, reshaping the entire biosphere and setting the stage for everything that followed. It is worth dwelling on the strangeness of this. The atmosphere you depend on, the very air that keeps you alive, is not a natural, inevitable feature of the planet. It is a product of life. It was manufactured, slowly and unintentionally, by generations of organisms so small you could fit millions of them on the head of a pin. Left to itself, without life, the Earth would have a completely different atmosphere, one you could not breathe for even a moment. The living world and the planet have been shaping each other for billions of years, locked in a partnership so deep that it is impossible to say where the planet ends and life begins. Life did not just survive on the early Earth. It rebuilt the planet in its own image, terraforming the world over billions of years, painting the atmosphere with the very gas we now breathe without a thought. This is perhaps the most profound legacy of those ancient organisms. They did not merely adapt to their world. They remade it, transforming a planet that was hostile to complex life into one where it could eventually flourish. In doing so, they wrote themselves permanently into the fabric of the Earth, in a way no later creature ever has. Every breath you take is a legacy of those ancient microbes, invisible ancestors who transformed a hostile world into a living one. And oxygen was only the beginning of how life reshaped the planet. Over billions of years, living things have altered the Earth in ways so profound that it is difficult to imagine what our world would look like without them. Life has shaped the chemistry of the oceans and the composition of the atmosphere. It has helped to break down solid rock into soil, creating the fertile ground on which forests and grasslands would one day grow. It has locked away enormous quantities of carbon in stone and sediment, quietly influencing the planet's climate across the ages. Even the great deposits of minerals and resources that human civilization depends on were, in many cases, laid down by the activity of ancient life. The Earth we inhabit is not a neutral stage on which life happens to perform. It is a world that life has helped to build, shaped, and reshaped by the ceaseless activity of living things across an almost unimaginable span of time. We do not simply live on the Earth. We are woven into it, and it into us, in a partnership so ancient and so deep that neither can be understood without the other. Every breath you take is a legacy of those ancient microbes, invisible ancestors who transformed a hostile world into a living one. And this brings us back to the deepest question of all. If life emerged so early, so quickly, and so stubbornly, and if it went on to reshape an entire planet, what does that tell us about the universe as a whole? Before we weigh those two interpretations, it is worth pausing to consider what the very atoms in your body have to say about all of this. Every atom, heavier than the simplest elements, was forged inside a star. The carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of it was cooked in the hearts of stars that lived and died long before the sun was born. Some of it was created in the cores of massive stars, then scattered across space when those stars exploded at the end of their lives. Some of it was born in even more violent events, in the collisions of the dense remnants that stars leave behind. That material drifted through space for ages, mixing into vast clouds of gas and dust, until some of it collapsed to form our sun, our planet, and eventually, you. This is not poetry. It is a literal, physical fact. You are assembled from the ashes of ancient stars. The story of life on Earth is, in this sense, just the most recent chapter of a story that began in the stars themselves. The universe built the ingredients, gathered them onto a young planet, and then, somehow, those ingredients stirred to life. Matter that was scattered across the galaxy came together, organized itself, and eventually became capable of looking back at the stars from which it came and wondering how it all began. When you consider that the same atoms now reading these words were once part of a burning star, the question of how life arose stops feeling like a distant scientific curiosity. It starts feeling personal, because the answer is also the story of you. There are, broadly, two ways to interpret the evidence written in the oldest rocks. The first interpretation is one of cosmic loneliness dressed up as good fortune. In this view, the rapid emergence of life on Earth is a stroke of luck so extreme that it may be nearly unique. Perhaps the conditions here aligned in a way that almost never happens anywhere else. Perhaps the origin of life truly is the great filter, and Earth simply won a cosmic lottery with odds so long that we may be alone, or nearly alone, in the galaxy. At first glance, the speed of life's appearance seems to argue against this. If life is so improbable, how did it arise so quickly? But there is a subtle trap in that reasoning. We can only ask the question at all because life did arise here. On the countless worlds where life never began, there is no one to notice the absence, no one to marvel at the empty silence. We necessarily find ourselves on one of the rare worlds where the improbable happened, simply because those are the only worlds where anyone could be around to wonder about it. So the swift appearance of life on Earth might not mean life is easy after all. It might only mean that we are, inevitably, standing on one of the lucky worlds, unable to see the vast majority where nothing ever stirred. The silence of the universe, in this view, is simply the sound of an empty cosmos. There is a strange comfort in this bleak picture, and also a strange responsibility. If we truly are alone, or very nearly so, then everything that has happened here becomes almost unbearably precious. The entire history of life on Earth, the whole slow climb from those first microbes to the mind reading these words, would be a singular event in a vast and empty universe. The awareness that has flickered into being on this one small world would be, as far as we know, the only place in all of creation where the cosmos has become aware of itself. That is a lonely thought, but it is also a reason for a kind of reverence. If the light of life burns nowhere else, then it falls to us to keep it burning. The second interpretation is far more expansive, and in some ways far more unsettling. In this view, the ease with which life took hold on Earth suggests that life is not a fluke at all. It is a natural consequence of chemistry and physics, arising wherever the conditions allow. If that is true, then the universe should be brimming with life, and the ingredients we find in meteorites and interstellar clouds are hints of a living cosmos waiting to be discovered. There is a single discovery that could settle this question almost overnight. If we were ever to find life that began entirely independently of our own, a genuinely separate origin, it would change everything. So far, every living thing we have ever studied is related. All of it descends from that one common ancestor, sharing the same fundamental chemistry. We have exactly one example of life to work with, and from a single example, it is impossible to say whether life is easy or hard, common or rare. It could be that life arises readily wherever conditions allow, and our planet is one of countless living worlds. Or it could be that the origin of life is a fluke so extraordinary that it has happened only once in the entire observable universe, and we are the improbable result. With only one example, we simply cannot tell. But the moment we find a second, independent origin, whether on Mars, on one of those hidden ocean moons, or on a distant world around another star, the picture snaps into focus. Two independent origins in one solar system, or even in one small corner of the galaxy, would strongly imply that life is common, that the universe is fertile, that we are far from alone. This is why the search for even the humblest microbe beyond the Earth is one of the most important quests in all of science. We are not just looking for company, we are looking for the answer to whether life is a cosmic commonplace or a singular miracle. A single cell, found anywhere beyond our own family tree, would be one of the most profound discoveries in human history. But this optimistic view carries a hidden sting, because if life is common, then the silence we observe demands an explanation. And that explanation may be that the great filter lies not in the past, but in the future. That intelligent civilizations are common, and that they consistently fail to survive. There is a wonder in this second view that is hard to overstate. If life is a natural consequence of the universe, then the cosmos is not a cold and empty stage on which we alone happen to stand. It is fertile. It is alive with possibility. Every star you see could be warming a world where biology has taken hold, where oceans teem with organisms, where the same ancient chemistry that built us is quietly building others. The universe, in this view, is not a graveyard, but a garden, seeded from end to end with the potential for life. And yet, threaded through that beautiful vision is the cold needle of the silence. If the garden is real, then something is keeping its inhabitants apart, or keeping them quiet, or cutting them short. The wonder and the warning are bound together, impossible to separate. Both interpretations, in their own way, are haunting. Either we are almost impossibly alone, or we are surrounded by a cosmos of life that hides a warning about our own fate. And the rocks, those silent, ancient witnesses, cannot yet tell us which is true. What is remarkable is that we can even ask the question at all. For almost the entire history of the Earth, there was no one here to wonder about any of this. The microbes that ruled the planet for billions of years never looked up at the stars and asked where they came from. The oceans and the rocks kept their secrets, recording the story faithfully but silently, waiting for someone capable of reading it. And then, in the final flicker of that long history, a creature appeared that could look at an ancient stone, measure the atoms inside it, and reconstruct events from nearly 4 billion years ago. We are the part of the Earth that has finally learned to ask about its own beginnings. That, in itself, may be the strangest and most wonderful development in the entire story. There is a deeper puzzle hiding beneath all of this, one that the ancient rocks force us to confront. What, exactly, is life? It sounds like a simple question, but the closer you look, the harder it becomes. We recognize life easily enough in the obvious cases. A tree is alive, a rock is not. But at the very boundary, in the transition from complex chemistry to the first living things, the line becomes blurry and uncertain. At what precise point does a collection of chemical reactions become alive? When does a bubble of molecules that copies itself cross over into being an organism? There is no sharp dividing line, no single instant we can point to and say, "Here, this is where chemistry ended and biology began." Life did not switch on like a light. It emerged gradually, through countless small steps, each one blurring into the next, until eventually something unmistakably alive existed where before there had been only chemistry. This is part of why the origin of life is so difficult to study. We are not searching for a single event, so much as a slow crossing of a threshold that has no clear edge, and it hints at something profound. Perhaps life is not a rare and separate kind of thing, standing apart from the rest of the universe. Perhaps it is simply what happens when chemistry becomes complex enough, ordered enough, and energetic enough, a natural extension of the same physical laws that govern the stars and the atoms. If that is so, then life is not an intruder in the cosmos, but a part of its natural unfolding. The universe, given the right conditions and enough time, may simply tend toward life, the way water tends to flow downhill. The ancient rocks, with their whispers of biology reaching almost back to the planet's birth, seem to hint at exactly this. That life is not an accident grafted onto a dead universe, but something the cosmos does when it can. What they can tell us is that something was here before us, long before us. Before the dinosaurs, before the first fish crawled onto land, before the first complex cell divided in the ancient sea, there was life. Simple, microscopic, and utterly tenacious. It clung to a world of fire and violence, endured bombardments that boiled the oceans, and refused to be extinguished. It pulled carbon from its surroundings and built the first fragile cells nearly 4 billion years ago, leaving faint traces in stone that would survive, against all odds, into our own age. We are the distant heirs of that ancient beginning. Every living thing you have ever seen, every plant, every animal, every human being, descends from those first microbes that took hold on the young Earth. The unbroken thread of life stretches back across billions of years, connecting you directly to organisms that lived on a planet you would not recognize. Consider what that thread has survived. It endured the bombardments that boiled the oceans. It survived the great transformation of the atmosphere, when a gas that was poison to much of the early living world flooded the skies. It weathered ice, ages that gripped the entire planet, and warm ages that melted the poles. It came through mass extinctions that swept away the overwhelming majority of species again and again. Through all of it, the thread was never fully broken. Life bent and shrank and transformed, but it did not stop. From those first fragile cells to the creature reading these words, the chain of living things has held, unbroken, across an almost unimaginable gulf of time. You are the living end of that chain, at least for now. The most recent link in a sequence that reaches all the way back to a world of fire. Every one of your ancestors, without a single exception, survived long enough to pass life onward. An unbroken record of success stretching back nearly 4 billion years, and ending, for this brief moment, in you. And somewhere in that deep past, in a time from which no rocks survive, lies the moment we most want to understand and cannot reach. The moment when chemistry became biology, when the lifeless became living, when something, somehow, took the first breath in a universe that had been silent since its birth. Everything that has ever lived traces back to that single, hidden moment. Every heartbeat, every growing thing, every creature that has ever moved across the face of the earth, is connected to it by an unbroken chain stretching across nearly 4 billion years. It is the deepest root of the tree of life, buried so far back in time that we may never fully uncover it. And yet the search goes on, because the pull of that question is impossible to resist. We want to know where we came from, not just as individuals or as a species, but as living things, as part of the great phenomenon of life itself. The answer lies in that lost moment, in the transition we cannot yet see, in the spark that lit the flame we all still carry. We do not know how it happened. We do not know if it happened here or was carried in from somewhere else. We do not know if it is a common event, repeated on countless worlds, or a singular miracle that may never be repeated. What we do know is that it happened astonishingly early, on a world that seemed determined to prevent it. And that stubborn, improbable beginning is the reason you exist at all. Perhaps that is the most staggering thought of all. That the faint chemical whispers in the oldest rocks on Earth are not just a scientific curiosity. They are the opening lines of your own story, the first words in a book that has been writing itself for nearly 4 billion years and is still being written today in you. Think of the sheer improbability of your presence here. For you to exist, life had to begin at all, against odds we still cannot calculate. It had to survive the bombardments, the frozen ages, the great transformation of the atmosphere, and the extinctions that erased almost everything. It had to make the difficult leap from simple cells to complex ones, and then, far later, to intelligence. Every one of those steps could have failed. At countless moments across nearly 4 billion years, the thread could have been cut, and you would never have come to be. And yet, here you are, a living being made of ancient stardust, descended in an unbroken line from the first fragile cells of a burning world, capable of reading a story written into the oldest rocks on Earth and recognizing it as your own. That is not a small thing. It may be one of the most extraordinary things in the entire universe. The rocks are still speaking. We are only beginning to learn how to listen. And the effort to listen more closely has never been greater than it is right now. Across the world, scientists are developing ever more sensitive instruments, capable of reading the chemistry of individual atoms locked inside ancient stone. They are venturing to the most remote and forbidding corners of the planet, to the frozen edges of the far north and the scorched deserts of the ancient interior, hunting for rocks old enough to preserve the earliest traces of life. Beyond the Earth, robotic explorers are searching the surface of Mars for signs of a second beginning, drilling into ground that has not been disturbed for billions of years. Plans are being drawn up to reach the hidden oceans of the frozen moons, to peer beneath their icy shells and sample the dark seas below. And far out among the stars, a new generation of telescopes is beginning to study the atmospheres of distant worlds, searching for the faint chemical signatures that might betray the presence of life on a planet trillions of kilometers away. We are living in an extraordinary moment. For the first time in the entire history of our species, we have the tools to begin answering questions that our ancestors could only wonder about. Where did life come from? Are we alone? Is the universe empty or full? We do not have the answers yet, but we are, at last, in a position to ask the questions properly and to go looking for the evidence. And every ancient rock we split open, every distant world we examine, brings us a little closer to understanding the deepest mystery of our own existence. The scientists who study these ancient stones are chasing more than a mystery about the past. They are searching for an answer to the question that underlies everything. How did we get here? It is, in a sense, the oldest question of all, the one that lies beneath every myth, every story, every quiet moment of wonder our species has ever known. For as long as there have been people, they have looked at the world and asked how it, and they, came to be. For most of that time, the question could only be answered with stories. But now, for the first time, we have another way to seek the answer. We can go to the rocks themselves and read the record they preserve. We can measure the atoms, reconstruct the ancient chemistry, and trace the family tree of all living things back toward its root. We can even look to other worlds to see whether the story played out elsewhere as well. The question is the same one our distant ancestors asked, gazing up at the night sky. But the way we pursue it has been utterly transformed. We are no longer only telling stories about our origins. We are investigating them, patiently and rigorously, gathering real evidence from a past almost too deep to imagine. And every time they think they have found solid ground, the story shifts beneath them, sliding further back into a past that grows stranger the deeper they look. Something was here before us. Something took root on a burning, battered world when all our instincts say it should have been impossible. And whether that something makes us cosmically special or cosmically doomed, whether it means we are alone or merely the latest in an endless procession of living worlds, is a question we have only just begun to ask. For nearly 4 billion years, the answer has been waiting, written in stone, buried in the oldest corners of the earth, and perhaps in the rocks of other worlds as well. We are the first generation with any real hope of reading it. That is a remarkable place to stand in the long history of our species, at the very threshold of understanding where life itself came from. The rocks are still speaking. We are only beginning to learn how to listen. If this journey into the deep past left you looking at the world a little differently, be sure to like this video and subscribe for more journeys into the cosmos. And as you go about your day, remember that you are not just standing on the earth. You are the latest chapter in a story it began telling itself almost 4 billion years ago.